Good afternoon, everyone. Today our speaker is Pawel Szewczyk, who is a PhD candidate at our institute and is working with Dorota Rosińska on neutron stars, and he will tell us about the dynamical stability of his sources. Pawel, the floor is yours.
Great, thank you. So thank you for the introduction. And yeah, so my name is Pawel, and I'm currently finishing my PhD here in the University of Warsaw, Astronomical Observatory. And today I'm going to talk about this project that we were doing over the last 4 or 5 years, mainly in collaboration with my supervisor, Dorota Rosińska, who is already here, and also another important contributor, Pawel Szewczyk from Valencia. So just wanted to mention them. So yeah, let's jump straight into the topic, because this is just want to warn you that this will be more theoretical than practical, than observational. And the topic about hypermassive neutron stars is I think in the era of multi-messenger astronomy and the recent observations of binary neutron star mergers and some hope for observation of gravitational waves from core collapse supernovae, things like that. This would be a very interesting topic these days. So so there is one. The first statement here is the thing that was kind of a motivation for the whole project. Namely that the fact that if you put a differential rotation into neutron stars, you can produce equilibrium solutions with much larger mass than that is possible for non-rotating case or rigidly rotating case. It was shown in 2017, for example, by Dorota here, and this motivated this work because of course we can produce equilibrium solutions, but we are not exactly sure what are the stability properties of those configurations. So here I'm going to try to answer those questions. First, what is the possible maximum mass, and how far can we go? And then
it would be good to face the audience so we can.
Yeah. I'm trying to do that. So this is going the main question. The main question I'm going to try to answer here is the stability of the configurations that are very massive. I will show how massive in a moment, and try to estimate some kind of stability, then limit, characterize it, and show the region where configurations are stable. That would be the goal. And then there is a question of what we can learn from this, and what we can learn from dynamical properties of hypermassive neutron stars. So just starting with putting this in some astrophysical context. There are actually 2 very important cases where when this differential rotation that I was talking about plays a very important role. And the first one is binary neutron star mergers. So when you have 2 neutron stars that are merged into something massive, there is a possibility that, and actually this comes out from numerical simulations, that usually you see that the rotation profile of the remnant is not uniform. This remnant is not rotating rigidly. Here on this picture on the right, you can see some examples of results from numerical simulations that show that the differentiality of this rotation is very strong. And actually, if you hear about the hypermassive neutron stars these days, I think people mostly refer to these binary neutron star merger remnants. And you can see in this picture on the right that the difference in the rotation velocity is very large between outer layers and some inner layers. But the other very important context is collapse of a massive core. So basically, a collapse supernova. Because then we also have a strongly differential rotation in the remnants. There are very important differences if you compare like remnants from binary neutron stars and core collapse. But here also on the right you see some example profiles of rotation that come out from numerical simulations. So those are the two main areas that we are interested in astrophysical sense. And we already seen gravitational wave emission from binary neutron star mergers. So this is a hot topic in observational science, and we are still trying to detect some core collapse emission in gravitational wave domain. But we have some work that may predict that there is high probability that if a supernova would explode in our galaxy, we would detect it with LIGO, for example. Yeah, so this was just some astrophysical context that will come back later. But now let's go to some more abstract and theoretical approach to this field. So let's try to discuss what is the maximum mass of a neutron star. This is something that is well known to any astronomer, that if you have a neutron star, there is a limit of mass. Basically, if you assume some properties of the matter, so the equation of state, you can produce this solution space, which is basically like a line, like here on the right. This is usually depicted like here. You have a relation between radius and mass of the neutron star, and those are non-rotating solutions. And usually there is this TOV abbreviation, which comes from Tolman-Oppenheimer-Volkoff equation, which describes this kind of object. And you see that there is a clear limit of mass. And this is one of the most pressing questions in studies of neutron stars. What is the value of this mass? And we are not sure exactly. We have some estimations. We know it's like at least 2, because we've seen neutron stars with 2 solar masses, or more than 2 solar masses. So I'm not going to go deep into that topic, but there are some rough estimations of this value, and it's somewhere between 2 and 2.5 solar masses. But this is not a rotating case. And what happens if you introduce rotation to this object? So it turns out that you can actually increase this limit by like 20%. Depending on the equation of state, it may be different, 15%, maybe something like that. But yeah, you can produce configurations that are more massive than the mass limit for non-rotating neutron stars, just by putting rigid rotation. And obviously, you cannot increase the rotation infinitely. There is a limit which comes basically from it can be called Keplerian limits. So this is the point where like at the equator you reach the Keplerian velocity at that point. So the matter would just be lost from the start, basically. So this is this limit in the red on this right picture. So what happens if you change this rotation to differential rotation? Turns out you can go even further. You can increase this mass even more. This is an example of let's say, one model of differential rotation. I will describe this A value in a moment. And if you pick a specific model of differential rotation, a specific rotation curve, you can see that you can produce configurations with even more masses. And those configurations that are more massive than this red point here, the limit for rigidly rotating configurations, those are actually the ones that are called hypermassive. So this is where the hypermassive term comes from. But the question is how far can we go with this value of mass? And this is where things become difficult, because we start to reach solutions which are well, some people may not even agree they are stars anymore, but we still consider them stars here. Namely, to quasi-radial configurations. So that will be very important here. So I want to explain this very specifically. If you increase the rotation to a specific point and have a differential rotation, you can reach configurations like this. On the left, you can see this meridional cut, so view like from the side, and this is on the right. You can see the equatorial plane. So basically a cut through the equatorial plane, and those are the maps of the density. So you see that the maximal density, those points here and here. So this ring here, the maximum density is not in the center of the star anymore, somewhere else. And if you would go further and further and further, you will actually reach a point where you have a hole in the center, so you have actual torus. And this was some discussion, but in this work we consider this the limit of the definition of the star. So if we are talking about neutron star, we limit ourselves to configurations which have this topology that is still spheroidal, that the surface of the star is still does not have the hole in the center. But like in principle, we could go there, but this would be a very different topic. So we reach those configurations, and it turns out that things are not so simple anymore, because on future rotation, you can think that you can describe a neutron star by two parameters. So you can pick, for example, a central density, and you can pick some, I don't know, angular momentum. That would be good. And you have exactly one equilibrium solutions for that. But in differential rotation, it's no longer the case. You have multiple solutions with the same parameters, and because of that, we use this classification into 4 types that have different characteristics, and here I will be talking more about type A and type C. I don't want to give you an exact definition of this classification, because it's not that trivial. But the point is that those configurations might have like the same parameter, the same astrophysical parameters, but look different. So they kind of coexist in the parameter space. And if we include those, we can increase the mass of a neutron star to absurd levels. Here you can see this stop line, which is value of 2.5 TeV mass, which is something like 5 solar masses already. So this is very large mass. So the question is how far can we go, and it was actually kind of answered. First, this is done for polytropic models, and you can see here that with Oh yeah, I see that now. That we increased degree of differential rotation. So think of this as the steepness of the rotation profile. With increased steepness of the rotation profile, you can reach even 4 times the TOV limit, which would be something more than 8 solar masses. Very large. And it was done also for some other models than one polytropic model. So it is universal across different realistic equations of state, so more sophisticated models. And also the same thing happened for straight stat, which is also very interesting. That depending on the model, we reach different values, but the general idea is basically the same. We don't really focus on type V in this work for different reasons, which is the most massive, but there is an argument that they are unstable anyway. We are more focused on this type A, which are kind of normal configurations, and type C, which are just configurations with very strongly differential rotation. So here, just a few words about the technical details of this work. There are a few probably important details. So we assume two things. First, what I show you here is done for polytropic equation of state with some gamma equal 2, so something like this, which is a simple model, but it shows some qualitative properties of the solution space very well. And recently we are working with some more realistic equations of state, but this is not shown here. And then we are using this model of rotation, which gives us these nice rotation profiles, which are just characterized by this one number, which just characterizes the steepness of the profile. So the 0 value means the switched rotation. You just have this is the distance from the rotation axis, and this is the value of angular velocity, right? So you have rigid rotation, and then you have more steep rotation profiles. And then we do we do numerical simulations of selected things. This is the last part. So in order to determine the stability properties of some configurations, we will do numerical simulations of them. Okay, so
So I'll ask you a question. Are all these curves compatible with the assumption that J is constant?
This is actually a very misleading name. This is why I recently tried to avoid it. It's I don't really remember. I don't really understand why the name is like this. Yeah. It's not J. It's not the J that we are thinking about. So it's not like J is constant here and the name is misleading. And if there is time, I will try to explain it better in the end. But this law is actually compatible with what we see for collapse remnants. Like in collapses, you usually see something like this. There is a problem with binary neutron star mergers because the remnant of this, actually the maximum, which here starts just at 0, is somewhere else. So if you remember the picture from one of the first slides, you had something like increase at first, and then only then decreasing value of angular velocity. So this is slightly different, but those new models are still new, and we are working only with this simple model basically. So first, before we go into any numerical simulations, into any computationally expensive work, basically, there are some estimations that we can use, and this is actually something we discussed recently and got some I think interesting conclusions. And there is this so-called turning point criterion, which just says that if you have a sequence of, let's say, constant angular momentum, sequence of configurations of constant angular momentum, at some point you reach a maximum mass at this sequence, and that there is an argument that this is the point where which divides stable solutions from unstable solutions. And this is very clearly visible for non-rotating stars. You have this point of maximal configurations, and this is actually the threshold to instability. And you can extend it to rigid rotation very easily. And you can set some limit of stability in the parameter space, which is just a line that is very easy to compute, basically. But it's not that easy because it gives a sufficient criterion of instability, not an exact criterion, which is not the best way. And there is actually an argument why this works. It's not very exact, but it's more intuitive, I think. If you look at this picture and think that okay, let's choose some specific value of rest mass. So all the configurations with this rest mass lie on this blue line, and also let's choose some value of angular momentum. So those magenta lights, and those are the things that are kept basically kept in hydrodynamical evolution, right? If you keep the properties of matter, those two things will basically stay the same. And you can see that for each pair of J and M, you can produce like two configurations. So two configurations with the same rest mass, the same angular momentum, and it turns out only one of them is stable. Yeah, I can do this. So if you think of just in a very abstract way, you have some mass with some angular momentum, and you have some hydrodynamical path that it will follow. And on that path, you have two equilibrium configurations. One of them will be stable, and this is the one that minimizes the energy, basically. So you follow this blue line, you reach the stable configurations, it's all good. But if you reach this unstable configuration, you'll probably go this way until you form a black hole. Anyway. And there are pairs that obviously don't have an equilibrium configuration. So those would be effectively on collapse to a black hole. Don't reach any equilibrium configurations of Neutron. So, and there is a critical point here where you only have one configuration, which is basically what was described by this turning point. Not going much into detail. We can see that in this parameter space, we are no longer using radius because it's not very convenient. It's better to use something like central density or maximal density in the star. Or in this case, we are using instead of density, we are using enthalpy. This H is maximal enthalpy in the star. We are using it because it's unitless value, so it's more convenient. But you can think of it as a density. In principle, it doesn't change. So in this parameter space, we can put this line where which divides the stable from unstable configurations. And for rigid rotation, this is rigid rotation on this picture, we can see that this criterion is actually sufficient for instability. So blue line, actually everything on the right is unstable, but it's not exact. So there is some approximation thing here, and this is for rigid rotation. And you can actually, in a more exact way than I've done right now, show that this criterion is actually a sufficient criterion for instability. There are proofs that do that. So this is nice. And if you look at differential rotation, it's much harder to prove this, and there is no like exact proof that this will work for differential rotation. So what we do if we select some value of A tilde and look at the starting point, but with one fix to this formulation that we see before. Because there is a difference between rest mass and gravitational mass, because we are talking about general relativity. There is some definition of mass is not that clear anymore. So we need to differentiate between rest mass and gravitational mass. The normal M here is gravitational mass, and M0 is rest mass, just to be clear. So turns out it's not that easy, and you actually need to look for the maximum of rest mass on these sequences of angular momentum fixed. That's an important detail there. Because depending on how you formulate the starting point criterion, you get 3 different lines. And if you keep this argument that they've shown with the hydrodynamical path, the central line is actually the correct one. And something like this was done by several people. This is an example of numerical simulations that test the dynamical stability of configurations with differential rotation. So an example, those green dots are stable solutions, the red ones unstable, and black dots are those turning points which should divide between stable and unstable solutions. And this work was limited to only configurations that are not quasi-toroidal. So they keep the maximal density in the center. And we expand beyond that, and we tested some more basically up to the mass limit configuration. So if we look only at the estimations of the stability and see different values of the degree of differential rotation, we can see that there are huge regions of stable solutions, and in particular the configurations with the maximum mass, the red crosses here, are usually on the stable side of things. So we can expect that the most massive configurations would be stable in that sense. So here is where the numerical simulations come in. So what we do is we get the equilibrium configurations that we calculated, and we just put them through simulated evolution by some existing more or less established tools. So we start with 2D simulations because in that way we are testing against quasi-radial perturbations, keeping away all the non-axisymmetrical effects. And this allows us to do a lot of the simulations, because if you are limited to only 2 dimensions, you can do a lot with small computing power. So we keep axial symmetry in this part, and then the main technical thing that is limiting here is that we are actually using something called conformal flatness condition, which is an approximation. It's not full general relativity. It is kind of approximated by this. And this is exact for non-rotating stars, but if we introduce more and more rotation, it becomes less accurate. But anyway, we are able to read some quite rapidly rotating stars. And it was shown to be accurate, for example, in terms of the mass that is calculated this way within 1 or 2%, which is good enough. So we introduced some radar perturbation to our solutions and see what happens, basically. And what happens is this. This on the left is what we are looking at to see what happens, which is the maximal density, value of maximal density, and how it changes with time. And you can clearly distinguish 2 cases. One, those configurations, the value is just oscillating, which means they just oscillate radially with some very clearly defined main frequency around like 1 kilohertz or something, or 300 hertz, and it's kept stable. And some configurations don't do that; they just collapse promptly to a black hole, which is shown here as a exponential increase in central maximal density. So we can see this clear division between stable and unstable configuration, which is shown here on the right side. The green dots are stable solutions, the red unstable, and we can clearly draw a line that divides those 2 worlds. And again, we can compare them to our turning point criterion, which is still shown to be sufficient, at least in this case. Actually, not for 3 ways we can form this. Yeah, so this is okay, and that was easy, and this is the hardest part, because here we reach some more extreme configurations, and in particular we reach configurations which are quasi-toroidal, which are very important for us because they were not studied before. So this is the thing that is new here.
Excuse me, are you going to explain to us what these dots are and the lines and the colors?
Yeah. This is a lot. I know. This is very easy plot. Like here, it's not much. You have the stable configurations. You have unstable configurations, and they are limited by 2 lines here. The bottom line is just a sequence of non-rotating configurations, right? It continues to the right and to the left, but it's kind of zoomed in to show the important features. And the red line is the threshold we estimate between stable and unstable solutions, right? And this area is actually area where all solutions should be stable. All configurations of these parameters should be stable. And we also compare this with this turning point criterion. Well, actually, the thing called general criterion is actually the important part here. The other 2 are just for kind of comparison. And the same thing is shown here, but there are 2 more things. And one, the colors are not rendered very well. So this is the line where which divides the quasi-toroidal configurations, which are those more massive, from those like normal configurations. And also shown here And the other line, the OAUW something, this will come later as a very important thing in terms of non-axisymmetrical perturbations. But for now, let's just focus on the quasi-toroidal network. So the part on the bottom of this line was studied before. It's kind of well known, that is, or more or less well known what's happening here. But the upper part was not studied before, so and we expanded this to this area, and we see that we can see stable configurations which are as massive as 2 TOV masses, 2 maximal TOV masses, which is like more than 4 solar masses. And actually, that the maximum mass that we can see in the solution space for a given model of rotation is still on the stable side. So we can expect those most massive configurations to be stable against those quasi-radial perturbations that we introduced here. Yeah. So this gives us motivation to go further, of course, because even if something is stable against quasi-radial perturbations, there is a good chance that they are unstable to some non-axisymmetrical effects. And those are actually interesting, because if you think about something rotating with like 1 kilohertz and being non-axisymmetrical, this is a very good source of gravitational waves. It means so something interesting. But just to put those results in some astrophysical context, let's just agree on some value of the maximal mass of non-rotating neutron star. Just say 2.3, just for the sake of this argument. And as I said at the beginning, there are two scenarios that are important for hypermassive neutron stars. And the first thing is binary neutron star merger. So here on the bottom axis is the rest mass of the configuration in solar masses, and on the y-axis it's a spin parameter that is usually seen in the results of numerical simulations of compact objects, which is just the angular momentum scaled to mass. So looking at different results from different groups of the numerical simulations, we can more or less know what are the typical values for the remnants of those of mergers. And for mass, it's pretty clear, because it's basically the range of typical neutron star mass doubled, right? So the lower part is just 2 solar masses, because at the lower end you have just the least massive neutron stars, which is something like 1 solar mass. And at the upper limit of the mass here is the case where you have just the most massive neutron stars that you can have, which is at this case 2.3. So we have 4.6 limit here. And you also can expect that in a binary neutron star system and during the merger, you have a lot of angular momentum. So we can expect that the angular momentum will be actually very high in the remnant, and it is somewhere in this area, 0.6 to 0.9. So this is the area, the rate of parameters that we can expect from the remnants produced by nature. And the other part, which is core collapse supernova, it's not that easy, because first, of course, there are typical values for those parameters, and the masses are usually low initially in the remnants. So the mass of the collapsing iron core is not that high, lower than 2 solar masses, but there are some extreme cases where it's possible to have much more massive core that is collapsing. even more than 2.5 solar masses. So there are some typical values, but extreme values may be also very important here because those may be the one that we can detect because they are more bright in some domain. So and also there is other thing that during core collapse, of course you form the initial neutron star, but during the later stages you accrete more mass. So you can basically go way above those 2 solar masses that you had initially, because of all the matter that you can accrete. But this, of course, takes time. So this is a matter of time scales, basically. And you can see how this compares to our results. This is the case for this moderate degree differential rotation, as a small. When this green area is the area where we can produce equilibrium solutions that are basically stable. So you can see it's covering some of the, for example, binary neutron star merger remnants box, but not all of it. But if we go to those small differentially rotating configurations, we can actually see that we can produce configurations with whatever mass we want, assuming that we have enough angular momentum to support them, and those will be still stable. So going further, I kindly ignored this TOVW parameter, which will become important now, because this is the ratio between kinetic energy and potential energy in this neutron star that we are producing. And there is this estimation that above this, something like 0.26, all the configurations are just dynamically unstable to non-axisymmetrical perturbations. So this is why we go to this region and try to test this and try to test some other properties of those non-axisymmetrical behavior of those neutron stars. So this is what we do in the second part. We basically do 3-dimensional simulations, some of them. In this case, we are doing this in full general relativity, and we are trying to test 2 things that are more or less known for differentially rotating neutron stars. And the first is this dynamical bar mode instability, which is this limit that I was talking about, and the other is what happens with low T over W, and the fact that some people shown that those are also unstable, but in a different way, different time scale. So we do like 20 milliseconds of evolution, and see something similar. This is the paper that was doing very similar thing for some extreme cases. And this is what happens with those very massive configurations that cross this threshold of dynamical instability. We basically form some ball kind of structure in a very short time scale. Here you see less than 4 milliseconds in the end. Those are the density profiles in the equatorial plane. So density maps, and so very quickly you reach this bar structure, and eventually it collapses to black hole. So yeah, 4 milliseconds. but before it does, it rotates with this non-symmetrical structure, which may be very interesting at some point. And we can actually measure this. This in this case is some kind of measure of ellipticity of the star for very different configurations from these parameters important here. The T over W from very low value like 14 to above this 26. And those two configurations that were above 26 actually we see that they are collapsed to a black hole. Like in the end, this is where we end simulation because we cannot follow this anymore with our resolution. So we actually prove that this is true for some degrees of differential rotation. And the interesting thing is what happens with the other configurations, because they develop some kind of instability, but they at some point they settle down, or the timescales are much longer than this dynamical timescale here. So it's still work in progress, and we are still discussing what's the impact of this and how could we treat this. But for sure, this is a probably very interesting thing in terms of gravitational waves, because we don't have something that collapses instantly, but instead we have some non-axisymmetrical structure that is rotating. So this is probably a good idea to test also gravitational emission from things like that. Yeah, and we also test some other features. In this case, not only this bar formation, but also sometimes we see this kind of deformation, which is not it's like M1 mode only. So only like one arm thing, which happens on longer time scale. Those are some examples, and this is the evolution of the deformation parameter of this specific mode of instability, which in this case, in all the cases, is rising, which is, I think we don't have yet a good and definitive answer of why this happens, and how accurate are our simulations after like 10 milliseconds. But this is definitely something that piqued our interest. So then we can go back and compare this dynamical threshold of instability. So the part where we promptly have collapsed to a black hole. So those are those yellow lines that limit our solution space here and here, for example. And as you can see, they limit the solution space on a quite large values of mass. And we can very easily produce configurations with 4 solar masses in any case that are stable both to radial perturbations, as we've seen before, and to dynamical non-axisymmetrical instabilities. So configurations that may lead to something like a delayed collapse to a black hole. So imagine, for example, a merger of 2 neutron stars with total mass of something like 4 solar masses. And of course, if you look at results from LIGO, this would be marked as something that left a black hole after it, right? The remnant would be considered a black hole. But actually, for some time, not a long time, but for some time, the configuration would be still a neutron star, and this after merger, for example, after merger signal in gravitational wave would be something interesting. Just a sneak peek to some existing work on gravitational waves from here. I think this is a very interesting result because this took some very more extreme configurations which collapse to black hole on some relatively short timescales, but produce enough gravitational wave emission to be detectable by existing or planned gravitational wave detectors if it happens in our galaxy. So you see the SNRs for different detectors, especially this last configuration, last model, which was very emissive at 10 kiloparsecs. So that's far, but this is something that we can work with. That it's if something like this happens in our galaxy, there's a possibility.
Subker and supraker.
Yeah, so this was the main part of this particular work was that you've seen this. I was talking about this parameter, right? J over 1 squared, right? So this is called sometimes a spin parameter, a curve parameter, and there is this cosmic censorship hypothesis, right? That you cannot have naked singularities, which effectively means that if you have a black hole, it has lower than 1 value, right? So you cannot have a black hole in a sense that we understand it with this spin parameter larger than 1. And here you can see that you have neutron stars which have larger than 1 parameter spin parameter. So they cannot just collapse to a black hole without shedding some of its angular momentum. And this is actually shown in this paper that those configurations which are this parameter larger than 1 are called supra-Kerrian models. And it shows that those are very interesting in terms of gravitational waves. And I think there is still a lot of work to do in terms of gravitational wave analysis of this type of objects. But just going to the summary of the whole work. So we see that there is this huge region of parameters that with very massive neutron stars, as massive as 4 or even 8 solar masses, which can be kind of stabilized by differential rotation. And here we show that we find stable configurations with 4 solar masses very easily. And also that if you consider the most massive configurations, and this region near the most massive configurations, they are stable against radial perturbations, which means that if they collapse by some non-axisymmetrical effects. And in the if you are talking about dynamical stability, the dynamical bar mode stability, which is this T over W26, is a limiting factor here. Yeah, and just something to look out for in the future is that those dynamically stable hypermassive neutron stars may become a very interesting source of gravitational waves, and there may be some good information that we may learn in the future. Yeah, and of course there are a few things that I totally skipped over here. For example, the timescale to this delayed collapse that I was talking about, which is actually not very well known these days. And of course, we totally forget about, for example, magnetic field in this work. So there are a lot of limitations to this approach, but I think we are getting some still very interesting results about the dynamical properties of neutron stars in this differentially rotating regime, and I hope we can get even more interesting results in the future. So I think this is end of my presentation, and yes, thank you for your attention very much.
We have any questions here, the audience? I wanted to ask about more challenging or more time-consuming factor in the simulations that you're doing. What's the
time was about, yeah, so of course it's the part where we need to do 3-dimensional simulations, right? Those are the most time-consuming, and I actually put it somewhere here that we are using I wouldn't say low, but moderate resolution of those simulations. I would really be happy to see more like higher resolution, higher numerical resolution in these simulations. So yeah, increasing the resolution in 3-dimensional simulation is actually very painful, because if you think that you have a grid that's, for example, 100 by 100 by 100, and if you want to double the resolution, so have 200 by 200, you actually don't. You actually increase it not by the power of 3, but power of 4, because time is also a factor. So it's very time consuming to increase the resolution there. So we had to compromise there a bit. Yes. And we wanted to see long simulations. You see the 20 milliseconds here. Those are like the machines that we are using, like a week of simulation.
Any more comments?
Maybe something on Zoom.
Do we have yet? Anything on Zoom?
I see Łukasz is, and
yeah.
How does it work? I want to see anyone else wants to see everyone.
So Łukasz, can you hear us?
Yes, I can hear you. I hope you can hear me. Just a quick question about the statistics. So do you have any clues on the numbers? What fraction of neutron stars in the galaxy can have these extreme rotations?
Yeah, I can repeat.
So we can repeat the question.
Yeah, because we have a speaker issue. So you're asking about about the statistics of how. I'm not sure if I understand you correctly. About
the fraction. What is the fraction of neutron stars we have in our Milky Way, let's say, which can have these kind of extreme rotations?
Yeah, this is because
the question is about the rate and the fraction of neutron.
Yeah, so the question is what was the fraction of neutron stars that could have these properties in our galaxy? And there is a very sad answer, because the properties we are talking about are the timescales are very short here. We are talking about less than days. So after a day of a live neutron star, we don't expect such high differential rotation, because there are some effects, like, as I said, magnetic fields or just sheer viscosity that would transform the neutron star into rigidly rotating one. So the time scale for that is very short. So it's basically the same as the rate of binary neutron star mergers and the rate of core collapse supernovae, where we can expect something like this, but of course, if you look at the distribution of parameters, for example, for binary neutron star mergers, this line that divides those radially stable from not stable basically cuts this box in half. So we can expect like half of them would be interesting and half would just promptly collapse to black holes. So there is an answer to that. And in terms of collapse supernovae, it's more complicated. And those are rare events, as you know. So not entirely sure. I hope that answers some part of your question.
Thank you.
Thank you very much. I don't see any more
I
questions.
see one question here. Or not. I'm not sure.
I don't know. Do we have any more questions? Professor Hensel?
Yes.
Oh, yeah. Yeah, you can ask.
Do you hear me?
Yes.
Yeah. So my question, well, it's question and comment. You use very simple equations of state. And in particular, as far as I remember, the merger that could produce such massive objects, they are also associated with very high temperatures and also with neutrino trapping. So that equation of state is not one parameter equation of state like you are using, and this criteria for stability refer to one parameter equation of state. And of course, magnetic field, differential rotation produces magnetic field, which also can be very important. So this is a comment, and now additional comment. So actually, I would say that it would be good to at least think about not one parameter, but more complicated equation of state, just to try it. And another comment is about the time scale of collapse. Of course, it is not exactly known, but I guess that the viscosity, which actually will induce collapse because of rigidification of this differential equation, differential rotation, is I think mediated by neutrinos which are trapped. So this is the source of angular momentum transfer within the merger, and I think it is seconds. Seconds, maybe 10 seconds, but this is it.
Yeah, there is a strong argument for what we are saying. So just maybe not everyone heard what you said. You bring out some very very important points here. So the first is that actually yes, if you consider remnants of binary neutron star mergers, or even probably more importantly core collapses, you have a very high temperature there. And we are totally neglecting the effect of temperature in this work. And I agree, this is probably if I would tell what is the next step here, it's probably this, considering finite temperature equations of state, and it was actually in the initial schedule of the project, but of course we had to cut some of the plans cut off. We are currently working on still cold but realistic equations of state, just to do basically the same results for not so simple equation of state as polytrope, but something more realistic. And the next step would be, yes, introducing temperature, effects of temperature. So this is a very strong, important point. And the other point that you brought up is neutrino, effects of neutrino trapping, which is also a very important factor in those events. But I was never an expert in neutrino, so I'm not sure if I can comment on that more specifically. More than what you said, and Yeah, and you said that in your opinion, because of those effects, because of the viscosity, magnetic fields, the rotation profile is rigifying, so it's going into just uniform rotation in matter of seconds. And this is what I was talking about. Why it's not that clear what is this timescale? Because there are some works that show that in collapse, for example, you can keep the differential rotation for a longer time because it's somehow induced by the accretion. So this kind of longers the time scale. But on the other hand, there are some works that show that was not apparent in the early days of simulating collapses, that if you look at a very small distances, you can have some turbulences and effects of some turbulent magnetic fields are becoming dominant in some cases, and this may even shorten the time scale on the other hand. So this is why it's not clear what are the time scales here, because there are many factors, as you said, temperature, neutrino emission, magnetic fields, viscosity, all those things. We are just not sure. But yeah, thank you for the comment, and I think of this work as just a first step, and in some sense this may be considered a toy model or something like this. But I hope in the future someone will do this more advanced way.
Thank you, Pawel.
Thank
Thank you for the comments, all the questions, and good luck with your work with finalizing your PhD thesis. And to everyone,
I think there is one question.
So maybe we can do it more like in a one-to-one chat, because we are late already. Time. Or the person that wants to ask a question, you can also write it on Zoom, and Pawel will reply. So thank you very much.
Or you can send me an email or something.
Thank you.
Oh.